So what is the principle of nuclear fusion technology using lasers, which was successfully developed by American researchers this time? The nuclear fusion technology successfully achieved by American researchers is based on the inertial confinement fusion method. Inertial confinement fusion involves using ultra-high power lasers to compress the fuel to a very small size, dramatically increasing its density. This results in the fuel reaching temperatures exceeding 100 million degrees, at which point nuclear fusion reactions occur. The specific principles are as follows. A fuel pellet consisting of deuterium and tritium is placed inside a hollow metal fuel chamber, hohlraum. Lasers surrounding the fuel chamber are fired simultaneously to focus on the fuel pellet. The impact of the lasers causes the fuel pellet to rapidly contract, leading to an extreme increase in density. The high-density fuel is heated to over 100 million degrees, creating a plasma. Nuclear fusion reactions occur in the extremely high-temperature plasma. Energy is generated as the plasma is released. The recent achievement by American researchers in using 192 simultaneous laser shots to detonate the fuel pellet is groundbreaking. As a result, the density of the fuel pellet increased by over 1 million times, and it produced 59 kilojoules of energy through nuclear fusion reactions, equivalent to 0.7% of the laser's energy. This research is being widely hailed as a significant advancement with a high potential for the commercialization of inertial confinement fusion technology. With continued research, it is expected that we could come one step closer to realizing nuclear fusion energy. However, there are still challenges that need to be addressed. The primary challenges include increasing laser output. Raising the output of lasers would allow for more efficient detonation of the fuel pellet. Increasing the density of the fuel pellet. Higher fuel pellet density reduces the energy required for initiating nuclear fusion reactions. Improving the efficiency of nuclear fusion reactions. Enhancing the efficiency of nuclear fusion reactions would result in more energy output. Once these challenges are overcome, laser-based fusion technology has the potential to become a practical and environmentally friendly source of infinite energy. The laser-based nuclear fusion technology successfully achieved by American researchers is based on the inertial confinement fusion method. Inertial confinement fusion involves enclosing the fuel, and then irradiating it with high-power lasers to cause the implosion of the fuel, leading to nuclear fusion. In this experiment, a fuel pellet consisting of deuterium and tritium with a diameter of approximately 1 millimeter was used. High-power lasers were directed at the metal fuel chamber surrounding the pellet, rapidly increasing the pressure and temperature inside the chamber. As a result, the pellet imploded, triggering nuclear fusion reactions. The energy produced through nuclear fusion reactions in this experiment amounted to 1.35 megajoules, equivalent to approximately 0.7% of the total energy used. While this level of energy production is not yet at the commercialization threshold, it represents a significant achievement, surpassing the key milestone of 1 megajoule set in the nuclear fusion roadmap for ignition. The advantages of laser-based nuclear fusion technology are as follows. It is compact and straightforward. Compared to magnetic confinement fusion reactors, it is smaller in scale and simpler in design, making it easier to construct. It offers flexible operation. It allows for control over nuclear fusion reactions by adjusting fuel supply and laser output. However, laser-based nuclear fusion technology must address the following technical challenges. Laser output enhancement. To initiate nuclear fusion reactions, higher output lasers are required. Fuel density improvement. To efficiently trigger nuclear fusion reactions, technology to increase the fuel's density is necessary. Stability improvement of nuclear fusion reactions. Nuclear fusion reactions cause a rapid expansion of the fuel, necessitating technology to maintain fusion reactions stably. The recent achievement by American researchers is considered a significant advancement toward the commercialization of laser-based nuclear fusion technology. It is expected that ongoing research will continue to address these technical challenges and develop practical nuclear fusion power plants. The laser-based nuclear fusion technology successfully achieved by American researchers utilizes the inertial confinement fusion method. Inertial confinement fusion involves using lasers to rapidly accelerate fuel pellets, increasing their density and temperature to initiate nuclear fusion. The specific principles are as follows. Fuel pellets composed of deuterium and tritium are placed inside a hollow metal fuel chamber, hohlraum. Lasers are directed into the fuel chamber, creating a high-temperature plasma inside the chamber. The high-temperature plasma collides with the surface of the fuel pellet, accelerating it. The accelerated fuel pellets collide with each other, initiating nuclear fusion. In this recent experiment, American researchers continuously fired lasers over 1,000 times, increasing the fuel pellet's density by approximately 1,000 times and raising the temperature to about 100 million degrees Celsius. As a result, nuclear fusion reactions occurred, and approximately 1.35 megajoules of energy were released. This represents a significant advancement, as it is approximately 10 times the energy output of previous laser fusion experiments. This research is viewed as a significant step closer to the commercialization of laser fusion technology. However, there are still numerous challenges to address before laser fusion technology can be widely adopted. Some of the key challenges include developing technology to further increase fuel pellet density, developing technology to sustain nuclear fusion reactions, developing technology to increase the output of lasers. If these challenges are overcome, laser fusion technology holds the promise of becoming a future source of limitless energy.